So let's get started. So today's agenda, I will be introducing supervised learning and unsupervised learning. Timur will be taking care of the rest, and he'll be talking about k-means analysis, PCA, and we'll take up any questions at the very end. So let's get started. All right, you guys definitely unmute yourself and identify the next 4 pictures. All right. Yeah. So what's this?
Cat. Dog.
Cockney Spaniel.
So are we good with? So what do we think it is? A cat or a dog? Someone said cat.
Dog.
Flowers.
Cockney Spaniel.
Grass.
Grass. Yeah.
Okay, fair enough. Okay, so I hear cat, dog, flower. All right, fair enough. What's this?
Cat.
Dog. Cat.
Bed.
Blanket.
Dog.
Okay, I heard more dog than cat. It's concerning, but okay. What's this?
Airplane.
Sky. Machine learning 100.
UFO.
That's an airplane.
Corvette.
Parked right beside McDonald's. I don't know. Just
Oh
guessed
my
that.
god, come on, Eric. And finally, what's this? I didn't hear anyone say this.
It's an airplane.
Come on.
Rental car. Oh,
Lightning
Bel Air.
McQueen.
I see
All
Bel
right.
Air.
Actually, train.
All right, sounds good. So yeah, so just to recap, this is a dog, right? This is a cat. This is a plane.
That timing.
A plane in the sky. But you can just say it's a plane for simplicity's sake. And this is a car. All right, cool. So why did I make you guys go through that pretty trivial exercise? Well, I wanted to talk about supervised learning. So basically, you guys were actually doing a form of supervised learning where you guys were able to, you could say predict, maybe not with great accuracy, but you were able to predict what these different objects were based on your previous experiences with these particular objects. By looking at the car or the plane, you can, if I was to plot some of these features, right, I would say, oh yeah, the number of wheels are 4 on a car, and there's 2 doors, weight is about 4,000 pounds. Plane is significantly heavier. It has wings, blah, 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 blah. Finally, I'm able to understand that this particular picture, just by looking at it, is a car. This particular picture, by looking at it, is a plane. And same goes for these 2 pictures over here. You may or may not have even thought about these features, but at the end, you were able to understand that, yeah, these different, these objects in these pictures are actually, a car, plane, cat, and dog. Awesome. So now I'm going to go through another exercise. Just by looking at these pictures of houses, right, and looking at the number of bedrooms, the number of bathrooms, the square footage, and the price, can you guys predict what the price of this house on the bottom right is? Just predict what you think it is. Just by looking at these different features.
Say around 2 million.
2 million, okay.
I'd say 1.8 million.
1.8 million, okay.
I
Maybe,
thought 2 million.
1.5.
I'd say 1.6.
okay, that's good. Maybe a couple more predictions.
Actually, no. I'm going back. I want to say 2.2 based off square footage and bedrooms.
Okay, 2.2. All right, so
it's in a different state or province and say 500,000.
fair enough. That's a good idea. I didn't include that, but I will say that I got all of these pictures from realtor.ca, and they're all from Oakville. So yeah, so they're all from the same place, Xander, but I think you're a little off, Xander. Anyways, the real value of the house, or at least for what it was listed for, is almost $1.7 million. So whoever said 1.5, 1.7, or 1.8, sorry, you guys got pretty close. I think I even heard a 1.6. So good job, guys. What we just did here is an example of another form of supervised learning, where you were able to understand what the different features were, or what the different observations were, right? and based on these features, make a prediction as to how much the price of this house is. Awesome. So just to wrap up, what supervised learning is you're using label data from a data set to predict an unknown future instance of something, right? You have rows and columns, or you have your data organized into rows and columns, the columns representing the features and the rows representing the observations. Now, supervised learning, as I showed you, is done in a very controlled environment. A controlled environment is, where you have a lot of power as to what exactly you're looking for. When I asked you in those two exercises, what is, for example, what is the price of this house, right? You guys were looking at specifically what could the price of the house be, or even what was that object called. You guys were trying to figure out what that object was, overall. So to sort of connect with those two exercises to supervised learning again, the two forms of supervised learning are categorical and categorical and numerical. Or in other words, you can classify data or use a regression analysis to predict a future instance of that of something. So I might have thrown a few different words there, but essentially classification is the process of predicting classes, labels, or categories of some data, which in the previous example was actually the cat and dog or plane and car example, where we have to identify specific piece of data that are non-numerical. The regression is actually by graphing. So we didn't necessarily graph this data, but you would actually have to graph thousands and thousands and thousands of listings to really predict what the price of that house could be using a continuous value. Yeah. So that's basically what supervised learning is. And just to kind of add another example, if you have a Lego training set, if you're given a set of instructions and said, okay, build this specific thing like a car or a house or whatever, you're given those instructions, you are given all the pieces. Your goal is to figure out, how to build that specific object. All right. So that's supervised learning for you. Now, the real interesting part, well, not that one is more interesting than the other, but the real place where there's a lot of, interest nowadays is the unsupervised learning. Now, unsupervised learning, on the contrary to supervised learning, actually uses unlabeled data to create a model. So the model is provided unlabeled data, and you allow it to work on its own to discover information or trends or patterns that are actually invisible to people. So if I was to give you, let's see, a bunch of blocks, right? And instead of giving you the instructions to say build a house, I give you a bunch of blocks and say build a house, right? I might have 100 different houses if I give that challenge to 100 different people, right? Because at the end of the day, I've built a house, but I've used different blocks in different ways to come up with that end result. So that's sort of what unsupervised learning is like. Now, as I said, you have an uncontrolled, and you're not controlling the environment, unlike the supervised learning experience. And at the same time, there's a lot more complex algorithms that are involved to come up with some of these trends and patterns and insights to the data that you're trying to analyze. Now, to analyze data in an unsupervised learning model, there's really four really common techniques that are used. The first is dimension reduction, which is basically reducing the number of redundant features to easily classify data. We'll be talking about that a little bit more. Now, then there's also density estimation, which is exploring the data to find structures within a data set. And then there's also market basket analysis, which is a modeling theory that suggests that if a certain group of people were to buy a certain group of items, they'd be more likely to buy another group of items somewhat relative to this particular group. So you don't need to know about that. It's just a theory. But what we're really looking at in this, especially for today's workshop, is clustering, which is a group of is basically a group of data points that are similar and most common, and it's pretty much put together in some sort of segment to find some common trends between these data points. A few examples that I've listed. One of them is If a bank wants to group its customers by a certain characteristic, whether it's age or credit repayment or whatever, it's just grouping its customers. Another example might be, and this is a pretty interesting project, is clustering DNA patterns to analyze evolutionary biology. You don't know what's happening in the back end, but you want to find different clusters and different commonalities between this data set so you can find these patterns and analyze them. So for a deeper dive into clustering, this is where Timur is going to take over, but that's sort of the introduction to supervised and unsupervised learning. Awesome. Timur, you can go for it now.
Yep. I'm just pulling up the slide now.
So what makes unsupervised learning more popular option compared to super? So it's not necessarily more popular. It's like if you're given data, if you're given a bunch of data, right? And you don't know what, and if you were asked to find trends in that data, right? By having that unsupervised learning model, you're employing one of those techniques that I listed in the previous slide to find the trends without knowing what you're looking for, right? So we're going to talk about how to do that in the upcoming slides. But it's not that one is more popular than the other. It's just they have different what do you call? I'm missing the word. Purposes. Yeah.
All right. Can everyone see my screen?
Yep.
Yeah?
Yep.
And everyone can hear me too?
Yep.
Awesome. All right. So we're going to be covering a type of clustering called k-means clustering. But before I explain how it works, can you look at this scatter plot and circle two distinct groups? Looking for a yes or a no. Anyone?
Yes.
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 Now, where are those groups?
The top left and the bottom right.
Awesome. So yeah, most people would circle these two groups. But our task is to somehow get a computer to also understand that these two groups are distinct and to classify these two groups. How does this work? Well, first, we choose a random point on the two random points. So first of all, we need to discuss how many clusters there are. There are two. So we choose two random points, and then we kind of go outwards from them and try to classify every point outwards from our first point, that what we call the centroid, until all the points are classified, kind of like this. Imagine these blue points are also classified. So once we've classified all these points, we take all of these points and we find the middle of all of those points, which is called the mathematical centroid. So we kind of reposition our first centroid, and we do the exact same thing again. We go outward from that point, trying to classify all of the data points around it to either green or red. And eventually, once we do this enough times, the centroid will stop moving, and we will end up with two distinct clusters. This is what it looks like when you do it in Python. As you can see, the gray is the centroid. The gray part of each cluster is the centroid, and the colors represent different clusters. Another really useful graphic is this one. So as you can see, we have the green, which is like no clustering. We introduce two random points. We start to classify with C. On D, we're already moving the centroids closer to the two clusters we're trying to find. And when we move them, we relabel or reassign all the points. And eventually, after enough cycles, we end up with the clusters that we want. And the key thing here is that you stop when the centroid stops moving. So you can imagine the centroid will first move fast and then start to slowly adjust itself. And past a certain point doesn't matter, right? So you just stop. Without further ado, let's jump into the Python notebook for this, for the week. So k-means clustering is a form of data analysis that aims to separate a scatter plot into a number of clusters. K clusters. So if we want 2 clusters, k equals 2. This is an iterative process where random center points for clusters are chosen. All the other data points are assigned to the closest cluster, the nearest mean, we call it. And a new center point is chosen at the center of the clustered points, and the steps repeat. Eventually, the cluster centers stop changing from iteration to iteration, so we stop the process. This notebook walks through a concrete example and then looks at applications in the Yelp dataset. So obviously, you guys know the drill. First, we import the libraries. For this one, it's quite different, so it's important that you import these ones. Also, we're going to be using the dataset, so I'm going to quickly mount my drive into here. Hopefully it loads. There it is. For our concrete example, we will use the makeBlobs function. For our concrete example, we will use the makeBlobs function to generate a data set with 150 points in 2 clusters. We put all of our points into a labeled data frame, so it's easy to see what we are working with. So here, this line generates a data set. For our concrete example, I thought it'd be okay just to basically artificially create a data set with 2 clusters with 150 data points. That's what we're doing with this line. And then we're making it into a data frame just to see what it looks like. So what does it look like? It looks like this. Each data point has an attribute 1 and an attribute 2. So a graph is going to look like that, 2-dimensional. And that's about it. This is what our data set looks like when plotted using last week's code blocks. If you remember last week, we covered basic data visualization. And that's what it looks like. There we go. By the way, I believe, oh, okay. So since there's no randomness in this, the data set will be the same every time, but we could have changed that. Now, we use the k-means function to create a k-means object with 2 clusters. Then we use the .fit function on our object to compute k-means clustering. Think of this as like us training our model. And then we use the predict. Oh, someone has a chat. Okay. Yeah. Then we use the fit function on our object to okay, I already covered that. Then we use the predict function to assign each point in our data set to a cluster. So this does all the computational stuff that I explained in the presentation. And it basically covers that part for us. To visualize our results, we plot the same graph as before, but now we add 2 parameters to our scatter. One denoting which points should be different colors. Oh, okay. One denoting which points should be different colors, and which color map to use. So as you can see, this code block is basically the same as this code block, except there's 2 extra parameters, namely C equals, which is the color parameter, and C map, which basically tells Matplotlib what colors to use, what different colors to use. So let's see what this looks like. Ah, looks familiar. So we've done it. We've computed k-means clustering. We know the clusters. Lastly, we can plot the actual center points of each cluster using the .cluster centers property of our k-means object. So here we plot what we plotted here, but after that, we get the centers and we plot them. What are centers? Just 2 points. 2 points, and we plot the 2 points. And we make them red. We make the size 200. That's That's this parameter right here, and we make the alpha 0.5, which means it's going to be like transparent. Boom. So as you can see, those are 2 red dots. That's our cluster centers for this data set. Now this is the fun part. This is the cool part. Get ready. Now let's try and apply clustering to our Yelp data set. Someone said something. Is the semicolon after plt.scatter necessary? Oh, sometimes people say to use it. Let's see if it works without. Oh, guess it doesn't matter. So let's load the data set in. Obviously, we've covered this last time. You need to have the data set added to your drive. It's in the public member resources. So we loaded the data set in. Good old trusty data set. Everyone remembers this one. The easiest demonstration of k-means in this case is clustering the points by their position on Earth. Let's plot what the data looks like before clustering. So this, you should remember this from last week as well. This is the points based on longitude and latitude. Yeah, pretty cool already, but let's see if we can cluster them. This code block is a copy of one seen early in this notebook. We just change the number of clusters to the needed amount and replace X with columns of our data set, reformat it to fit the model using 2 NumPy. To reuse this code block, change the number of clusters in the first line and the names of the columns denoted within the quotation marks. Now, I'm going to ask you guys, how many clusters do you think our longitude latitude data set has in terms of longitude and latitude? How many should we have? Josh says 3. Feel free to unmute yourself. 3. Everyone says 3.
That looks like 3.
You guys remember there's like 200,000 points in here, right? It's not just like
I say there is 10.
10?
10. I'm going with 10 here.
Going with 10. Okay. Anyone else?
I'm saying 5.
5. 18. Yes, Fahimi, you're right. We can set an amount of clusters. That's what we're trying to do. I decided not to reveal the number, so I just change this number. So 3, 5, 18. I'm going to go with 3 for now. Let's see what that does. So we changed that to 3. We changed everything else. Let's run this. And next, we plot our data once again, but this time with the colors assigned to each cluster. And so we plot this exact thing, except we do the C for colors and C map again. And we also change the size. So let's see what it looks like. 3 clusters. Are you guys ready? Let's see. Let's see if it works. Boom. 3 clusters. We have now, is this good though? Do you guys think this is adequate? Because personally, I think there should be more clusters.
I'd like to see what the machine thinks if you tell it to use more clusters.
Okay. I personally, when I counted these clusters, I envisioned actually I counted 13. So let's try 13. So we run this code block. We'll run this code block again. Boom. I think this is better actually, because if we zoom in, you can see that all of North America is now actually categorized. It's not just all of North America, it's Canada, which is in blue up here, Toronto, Montreal, and then parts of the US. But as you can see here, this cluster isn't very well separated, which means the actual number of clusters is 12. We can also keep visualizing each cluster, which cluster each point belongs to, even if we don't plot based on location, because we computed the clusters separately. Check this out. Now I'm gonna I'm going to plot all of the points, but not based on latitude and longitude. I'm going to plot them based on stars and review count, except I will keep the color classification. Let's see what happens. Boom. All right, so what do we see? We see that there's a lot of Canada, or a lot of this blue in all of the star ratings. And we can see that there's a lot of purple as well. But the point is, you don't have to be, you can cluster based on one thing and then plot based on a different thing and still have the colors show up, which is, I think, is pretty cool, you know? So yeah, think about useful applications for this would probably be if you say you figured out that, okay, so consider that this Yelp data set isn't actually all restaurants, right? The restaurants, whether or not it's a restaurant, is contained within the categories. Oh, within the categories of this data set. See, this is a gun store, for example, in North Carolina. And what if you clustered based on, well, what if you found a way to cluster based on whether or not it was a restaurant? And then you could evaluate something from there. But yeah, that was clustering. Any questions? I think this is really cool. Whichever one is the 1-star lime green with about 1,000 1-star reviews. Yeah. Let's see where it is on the map. Lime green. Like right there. Or here? California? Not sure. Or is that? Yeah, I don't know. Anyway, you could probably find this somehow. That was clustering. Now let's move on to the next bit. Principal component analysis. So this is a bit more of an advanced technique, but I think it's still cool to talk about, and maybe it gets your feet wet, you know, for this kind of stuff. So first, let's talk about the dimensionality of data. What are the dimensions of the 3 data sets that are in front of us? Who can say what's the dimensions for the one on the left? How many dimensions are there?
It's 2D.
2.
There's 2. So this one has 2 dimensions. And obviously the one in the middle has 3 dimensions. But what about this one? How many dimensions does our Yelp data set hold? If our df.shape gives 209,014, how many dimensions is our data set?
2, I think.
Still not those numbers multiply together.
Okay, so we got a huge number that would be like a lot.
Think about features of the data set.
Yo, I'm going with 5.
All right, Jeff's going with 5. Fahim says 14. Emma says 14. The answer is actually 14. There's 14 dimensions to the data. Each data point has, 14 features. That's what we call a dimension. And this is kind of introducing the idea of dimensionality to data. So obviously there's no visual for this because you can't really visualize 14 dimensions. But I thought it just introduced the idea. Okay, now that we got dimensions out of the way, what is variance? Can someone tell me, based on, I'm not even going to give you a definition of variance, just like intuitively, which of these graphs has the most variance?
The third one.
The third one?
Yeah, the third one? All right, you guys were correct. The one on the left has not a lot of variance. The one on the right has variance. So from a very simplified standpoint, very like layman's terms, we can say that the variance is how spread out the data is, okay? I think that's fair. Now, oops, shouldn't have said that. You can also think about it in this way. If we were to cluster, try and do k-means analysis on each of these, which one would be most successful?
Last one as well.
3? I see 3, I see most right, okay. So we can also say that the variance corresponds to how much information the data holds, because if we were to cluster it, for example, or classify it in any sort of way, it'd be much easier to classify a data set with more variance than it would be to classify a data set with not a lot of variance, because these points could be closer together and could be basically on top of each other. That's what we're thinking about. We're thinking about points on top of points. So we can't really classify points that are on top of points, but we can classify points that are not. That's the idea. Now, I'm going to ask, which axis on this graph gives the most information about the data? So which axis on this graph gives the most variance? Or has the most, you know, both y, x? You've seen some x? Okay. Well, I'm here to say it's neither. So it's actually not, the axis isn't labeled at all. So think about it this way. The x-axis only has this amount of variance, okay? And the y-axis only has that amount of variance. But if we were to stop thinking about which axes are labeled, the axis with the most variance is actually these two. Because this variance is definitely larger than that variance. So given that, we can basically change the axis of our data and give that to the clustering algorithm. So we rotate the entire thing, make these the new axes, and this is what we call the principal components. So what do? We took axes, we found the axes that had the most variance, and we just took those instead of the original ones. Now, the trade-off here is that if you knew what the x-axis and the y-axis meant, for example, position over time or something like that, you now have no idea what these new axes mean. These axes mean nothing to you. The computer just told you that these axes give the most variance, and therefore these axes give the most information about the data. Okay, so what's the procedure for a principal component analysis? How do you do it? Oh, whoops. Well, first you standardize the data. So we make the range of the data from 0 to 1. Then we see which variables correlate with each other the most. This is for an n-dimensional data set, not just 2 dimensions. Which variables correlate with each other the most? Is it stars in review count, or is it longitude and latitude? What is it, you know? Then we create the new axes that are basically all linear. This is the hard part. We create the new axes that are linear combinations of the original variables. Those are the new axes. The new axes are some amount of the x-axis and some amount of the y-axis put together. That's our new axis. And then after we created all of those axes, we end up, say for a 14-dimensional data set, we end up with 14 different axes, except the thing with PCA is the first 2 axes will always have more information than the rest. So the first one has more information than the second one, which has more information than the third one, which holds more information than the next one. So they're all ordered in terms of variance, with the first one giving the axis that accounts for the most variance. Therefore, if we wanted to reduce the dimensions of our data set from 14 down to 2 or from 14 down to 7 or something, we could just throw away the axes that don't account for that much variance. and we'd still have a lot of the information, and we'd be able to cluster it, and we'd be able to classify it better. That's PCA. That's quite a mouthful. So it's okay if you don't completely understand. This is also not meant to be an in-depth explanation. I can link articles afterwards if you really like one. I think this stuff is pretty crazy. Cool. So let's give a concrete example. Say we did PCA on our 14-dimensional data set, and we happened to come up with 14 of these axes, and somehow we also knew that each axis represented this attribute. Which variables would you throw away from our data set if we are evaluating the business success? Business ID, okay. So Fahim said business ID. What else would you throw away?
Latitude, longitude.
Latitude and longitude. Do you think, based on how we clustered latitude and longitude, do you think latitude and longitude would worsen how easily our data is clustered? Maybe. So we throw away longitude. Good for children. Okay, so we throw that attribute away.
Remember, you want to this is a unsupervised model, so you want to allow the model itself to discover info that's invisible to us. So keep that in mind when you're thinking of what to discard.
City and state. Oh, sorry. Okay, yeah, so we throw away city and state as well. What are we left with? Well, what I would throw away, oh, someone's answers more. You could keep longitude and latitude, get rid of city, state, postal code, etc. Yeah, pretty much. What you're trying to keep, what you know you want to keep, is things that you know are important. Well, for us, it's not always the case that we know what's important when classifying certain things. So this PCA thing will allow us to basically make a good, like, remove all of the data, or reduce the dimensionality of the data in a way that doesn't lose that much information, but helps us classify things. So onto the notebook. Principal component analysis is used to reduce the dimensionality of data and break it down into fewer, more important attributes that allow for better data classification, such as clustering. In PCA, we first figure out which variables correlate with each other, then create new axes for the data that maximizes variance. These axes are called principal components. We then use these axes instead of the old ones to do further data analysis, which could be like clustering or machine learning, classification, etc. As always, we start with the libraries. It's always the libraries. Load in the libraries. And for our concrete example, we will use the well-known iris dataset, which classifies 3 different species of iris based on characteristics such as sepal length, sepal width, petal length, and petal width. I only know 2 of those. I don't know what sepal means. Apparently, it's a way to classify different species of plant. So let's load it in using datasets.load iris. Visualizing this dataset in 3D, we see that in its regular form, it's easy to cluster the versicolor species, but hard to cluster the Setosa and the Virginica species. Those are the 2 different species of plants. So here we go. Don't worry about knowing how a 3D visualization works. Most of this is just adding the labels and removing the axes. It's not, most of the actual stuff is within these 3 lines and these 3 lines. So as you can see, we have the Virginica labeled as black, versicolor labeled as gray, and Setosa labeled as green. Now from this angle, it would be easy to cluster Setosa, but it would be a little more difficult to cluster Virginica and versicolor. And if we change the angle, we can see that, yeah, Setosa and Virginica are pretty much difficult to cluster, and versicolor is on its own. What can PCA do about this? Well, let's run PCA on it. Then we run a PCA analysis on the data set and take the 3 most important components and transform our data based on them. We are choosing new axes for the data that spread it out more. Once again, the 3 most important components would be the three axes that spread out the data most, which allow us to do better clustering, easier clustering. So we run the PCA. Let's see what we get. Boom. So immediately you can see that the clusters are more separate and they're like more equally distanced. Let's change the angle. Yeah, see? It's not perfect, but it's definitely better. Can you have there be a third indicator based on confidence or something? What do you mean by indicator, Xander?
Well, I mean, you already had them colored. That's why I just meant like I was thinking color in my head, but if color's already being used, so I guess something else to indicate confidence.
Well, in this case, we're actually not predicting anything. We're just seeing whether it would be easier to predict or not. That's the idea of PCA. Because if we gave a machine learning model this, it would have a difficult time. But if we gave a machine learning model this, it would have an easier time relatively, right? Or a clustering algorithm rather than machine learning, you know. Let's try applying this to our data set. Let's see if it works. Hint, it's difficult. So it might not. So there's a data set. We loaded it up just like last time. First, we cluster the data to classify it. If our PCA works, then these clusters should still be easily distinguishable. What does that mean? That means that we already knew that our data is pretty much classifiable. So our PCA should only really improve that. It shouldn't jumble any of the classifications at all. So here we go. We cluster just like the previous notebook, and let's visualize it just without the PCA, just visualizing it just first. What do we get? This might take a while. Once again, 200,000. Oh, that's what it looks like. What this is, the third dimension here is stars. So the star rating. This is basically the map that we saw in this one. This is this, except in 3 dimensions, essentially. And when we run PCA on it, honestly, for this application, it shouldn't change too much, but you will see how the axis changes, which is the important part for you to understand. So we run PCA on it, which is just another code block. Let's see what it looks like. Boom. So as you can see, PCA did spread out the data more. It turned everything from a column to a kind of like this looking line thing. And even though this wouldn't have a real application in terms of we give this to a clustering algorithm that has an easier time, it does show exactly like what PCA does, essentially. Because now instead of the axis being like this, we basically rotated everything this way. So yeah, not too remarkable, but it shows that the PCA did spread out the data a little more. This is not so much a useful application of PCA as much as it shows how PCA changes the axis of the data. You can almost see the old axes. A real application of PCA in our case would be challenging, needing more quantified variables and different classification. So not just location, such as whether the business is a restaurant, which is the issue that we're focusing on. We're running low on time, so I'm gonna end this quickly. This lesson might have been super duper intimidating, and maybe you're thinking like, well, how am I supposed to figure out how to do PCA on our Yelp data set? And I'm here to say a lot of this is exploratory. It's not necessary for you to do for like it's not necessary for you to necessarily do PCA. For example, what you could notice is that most businesses in our data set are actually not restaurants. So maybe you start by classifying whether or not each business is a restaurant. Okay, so you classified everything as a restaurant or not, figured that out. And then maybe you plot all of the, like, you find two variables and you find that if you color the restaurants red and the color the non-restaurants black, you get two clusters. Or you have like something of that vein. And then you can basically predict whether or not a business will be a restaurant. What is this useful for? You could also, after you figured out which business is a restaurant or not, you could compare other traits. For example, whether a business gets more reviews if it's has more hours worked or more hours open throughout the week, which is another kind of thing you can look into. And none of that has to do with PCA. It's a lot more simple. This is meant to, get your head thinking, expose you to these kinds of concepts. I think it's super cool.
Mhm.
Yeah. Any questions? No questions?
Think you did well, Timur.
All right. Once again, this list was supposed to illustrate that you can basically figure out if something is a restaurant if its categories include the word restaurants.
Mm-hmm.
So
Yeah, the PCA is a little bit more complicated. Yeah, it's developed by some incredible mathematicians, and yeah, it's beyond. Yeah, but if you are interested in, understanding how, how a lot of these businesses, especially in, these evolving industries that are continuing to increase how much AI and ML they're implementing in their, businesses, these types of things are very, um, these types of things are very common in terms of your typical ML or ML implementation or ML modeling practices. But yeah, for case two specifically, we won't be using PCA.
or you don't have to. It'd be
Yeah.
awesome if you found like a legit application, but we understand it's maybe out of your scope. So
Yeah.
do whatever you can. Maybe find a different, like just simpler data analysis, just an observation, maybe
Mhm.
maybe a linear regression of some kind.
Yeah. Yeah. 14. Yeah, exactly. Yeah. So week one stuff is somewhat more of the expectation. There might be 2 or 3 dimensional data that you could technically be able to compare, but even then it might get a little technical, mathematical. But yeah, it's just more of general knowledge to help you understand what ML is really all about, making those complicated concepts a little bit more easy to understand. You may or may not have understood it, but at least now you would have heard it for the first time. Yeah.
All right, and I guess that concludes our workshop.
Mm-hmm. Yeah. So once again, guys, the presentations for case two are next week. Take a look at the project expectations, which is posted on the Discord. I'll post it again today as a reminder. One thing I would like to say is this also goes for the chapter leaders. Most of our communication is going to be hosted on Discord specifically. I'm trying to sway away a little bit more from emails unless I need to reach out to specific people. It's also easier to communicate with each other as there's a very centralized community that's there. So if you haven't joined Discord, join Discord already, and that way you can get to know other people that are on there, and yeah, we'll keep in touch. And otherwise, once again, the presentations are next week, same time, 5:30 to 6:30. We'll We'll make sure that there aren't any technical problems this time. But yeah, that's about it for today. Awesome. So if that's all, then hope you guys have a very enjoyable week. And if you guys have any questions about your projects, whether it's content or the technical or even the presentation side of things, do use Discord. Discord is very helpful. Yeah, so it's, my parents keep saying get off Discord, but in this case, Discord is very helpful. There's always a community. Yeah, we're always here to help you. So make use of it. Definitely make use of it. Awesome. Hope you guys have a wonderful time and see you guys next week.
Bye, everyone.
Bye, guys.
Bye. See ya.
See you guys.